Okay, so what we discussed so far is the origin of bands. Now we are going into the plot of EK relationship for an electron in the crystal. Okay, so usually this is done by using some numerical method, because only then you will be able to get the exact shape correctly. But one thing you can notice is that as E increases, you will see that the bands are more and more wider, and also the separation between the bands are also becoming okay. Actually, if you draw it very accurately, maybe this peak here initially the peak will be larger, because this amplitude, maybe I need to correct a few things here. So the peak here will be smaller than the previous peak, because as you go increasing energy, the peak reduces because there is an alpha in the denominator. So this will be smaller, and one of the effect of this being smaller is that the region, or the forbidden region, the energy which can't be allowed because there is no solution, that will reduce as you go in increasing energy. So when you manually draw it, all of this to keep in track is a little bit difficult. So let me just modify it like this. Okay, so this is our -1, and this is our +1, and then we have middle region. So what I mean to say was this peak will be shorter and shorter as you may not be that much, like this, and then you have this taking a longer period. So I'll try to maybe show a numerical solution, because correctly drawing it by hand, you may not get exactly how things are. Okay, so this is somewhat like this. Okay, so the peaks here, so this peak compared to this, it will be reducing. So first peak was more, so you have a more wider region, and then that width also reduces. So these are some. So the next band will, it will come closer. Okay, and the bands will get wider also, because we are plotting it with respect to E. We are plotting it with respect to E, and E enter into the function as square root of E. So as energy increases, there is slope of this going smaller and smaller. Here you have more steeper slope, so the width of the band is smaller. So those kind of details are there, which if you want to get it correctly, then you have to do this numerically. But nevertheless, I'm trying to give you a flavor of this without losing much of the details by drawing with hand. Okay, so next thing that I'm going to do is basically the band structure. So band structure means the EK relationship. So band. So earlier we have plotted the band structure of free electron. So now it is band structure of single crystal. Now that is what is more important for our course. How does the band structure of the crystal, which is in our particular case it will be silicon crystal, how does that look like? Okay, this is not silicon, this is just our 1D crystal, but it has all the aspects which are important for us to know. Okay, before we draw the band structure, let me also say that the K is the phase factor in the block wave function. If you remember, the block wave function, that means our phi of x plus a, we wrote it as let's write it nicely, phi of x plus a is related with phi of a, like this. Okay, so this is what one way of writing block function, or in other words we can or alternate way is like we can say that this is phi of x, sorry. So another way we can write is phi of x is equal to e raised to I kx into u of x. So these are two equivalent things. Okay, it is actually saying the same thing. The wave function, the energy eigen functions. Okay, here phi is basically the energy eigen function. We are saying that it will take this particular form, that is the energy eigen function will have the above form. Okay, so if it has this form, okay, this particular form, so this is basically called the block wave function. Okay. So block wave function is basically exploring the periodicity property of the crystal. Okay, so if there is a potential which varies periodically, then it should have a wave function of this particular form. That's what basically the Bloch's theorem says. Okay, so if it has this form, then if you shift it by x plus a, then you will have e raised to jk x plus a and u of x plus a, and u of x plus a is a periodic function where u of x is a periodic function. So there is a linear phase and a periodic function. Now, so k is entering like this. Okay, k is entering to our solutions or our conditions that we are looking at through this Bloch's wave function. Okay, it is the phase factor. Now k, we have not restricted its value, but the values which k will take, as you can see, since it is a phase factor, if this phase factor goes more than for example pi by L, okay, then what is going to happen is it will, okay, so let's replace k with so k is a phase factor. So we have so Bloch wave function, we have phi of x is equal to e raised to j k x u of x. Now what I am saying is that if k varies to say k, so let's say some particular value k naught and k naught plus 2 pi, k naught plus 2 pi, what will happen to our wave function? So psi of x is equal to e raised to j k naught plus, so k naught was our initial factor or value of k. Now I increase it with 2 pi into x u of x, so which is basically e raised to j k naught x into u of x. The other factor that comes out is basically e raised to j 2 pi x. Okay, so so if I take this so when k is shifted from k naught to k naught plus 2 pi, then what happens is that we have a phase which is equal to 2 pi into okay, I think it is better to take the other expression of the book to see it even better way. So I have written two expressions. They are basically connected. So if you shift it by 5 of x plus a equal to, okay, so if I take that, so or alternatively we can say, alternatively 5 of x plus a is basically e raised to j k a into 5 of x. Okay, so now if I put same thing, k naught going to k naught plus 2 pi, then what will happen? So this will result in e raised to j k naught plus 2 pi. K naught, okay, so let me k naught into, okay, so 2 I'll write here 2 pi by, okay, so let's, I'm trying to say something very important. Okay, so if I shift k naught by k naught plus 2 pi by a, so then here it will become this into 5 of x. So this is going to be basically e raised to j k naught a 5 of x. So this is what I wanted to say, but okay, so we can ignore the above thing, so that it is not very clear. Okay, both are same relationship. One can be, you know, derived from the other. We have shown that in the previous class. So let me just shift this little bit up. Okay, so this is what I'm trying to say, that so if I take the block function, and block function has a phase factor k. So when the value of k goes from a particular k value, and when it is increased by an amount 2 pi by a, then we get the same block wave function. Okay, we get the same block function. Or in other words, what we can say is that, therefore we can say k naught and k naught plus 2 pi by a correspond to same k values. They are not different k values. Okay, so k value, the value which k can take are actually only in a range from 0 to 2 pi by a, where a is the period of the lattice. Okay, so that is another way of saying it. So in other words, k can take distinct values only in the range spanned by 2 pi by a. So this is the range. So either it can be from say 0 to 2 pi by a, but what is more common, or you can say minus pi by a to plus pi by. This is what is more commonly used. Okay, so k can take values from 0 to 2 pi by a, or you can say minus pi by a to plus 2 pi by a. Anything beyond plus pi by a will, you know, come back to negative values. Okay, they are equivalent. So just like I have shown here, if you start with some value which is negative, and you add 2 pi by a, you will get some value which basically comes back to itself. Okay, and this is not just with 2 pi by a, any multiples of integer multiples of 2 pi by a also, it is the same thing. Similarly, so I can add that also. Similarly, k naught is same as say 4 pi by a, 6 pi by a, etc. Okay, so there is a periodicity with respect to the value of k. So k cannot just simply go on increasing and this is also evident from our diagram here. If you look at here, I have put two limits for k values. One is -1, and when is cos k a is -1. So cos ka is equal to -1. The ka is basically equal to pi. Okay, ka is equal to pi. Then cos pi is -1. Then 3 pi. Then 5 pi, like this. These are the values where cos ka is equal to -1. Similarly, cos ka is equal to +1. What are the values? Ka is equal to 0. Then 2 pi. Then 4 pi, etc. So, so initially we can say that this point, the left point where you start getting solution, that is basically 0, k equal to, or ka equal to 0. Then the end of the solution where k cos ka is -1, you can say this is your ka is equal to pi, or you can say k equal to pi by a. And this one is also ka equal to pi, and then you go to pi to 2 pi. So these two heads corresponds to 2 pi. Okay, because it's the same point as far as the ka is concerned. You have gone to +1 and now you are coming back. So these 2 point again, this is going to be 3 pi, and this and this point, it goes to ka. I am writing ka. Okay, I can write it in terms of k also. So, or you can say that k is equal to 0 pi by a, then 2 pi by a, etc. Okay, and similarly here also I can say pi by a, 3 pi by a, etc. So these are the things that we need to keep in mind, that although k varies, so there are two different ways of plotting. One is like without taking into account of this. So that is how we will plot first. Without taking into account of the periodicity, we can plot, and the other is like taking into account of the periodicity. So now I am taking k here. I can take either k or ka. The first thing is that let me just put down the free particle ek relationship. So vertical axis is now E. In band structure we have a plot between E versus k, and we have a solution like this. So this is a parabolic solution. Okay, this is for free particle, okay, which we have already seen. That is not our case now, which we are interested in. We don't have all values of energy, we don't have solution. So what we saw is that earlier energy E equal to 0, we had a solution for free particle, but now when you introduce the impulse functions or the delta functions periodically, then what happens is that the minimum energy is shifted to a point corresponding to kx equal to 0 point is now shifted to a higher energy. So let's say that that higher energy is somewhere here. So this is the point from which you are going to have solutions, and then for a particular band, say from here to here, you are going to have solution. So if you plot the K and the E graph, so the way it is going to look like is it will be flat here and it will be flat here also. So again, if you do this numerically, you will get this exactly as I draw here. This side it will be flat and then it will come like this, okay? And then you have a gap in energy, right? If you look at here, you have a gap in energy. There is a forbidden region between these two Ka equal to pi and Ka equal to pi. So there is a lot of energy for which you don't have any solution. Okay, so there will be a gap, and after that gap, then again you will. So let me put that gap like this. Say there is a forbidden gap. So let's say this much is the gap. Okay, there is no, and then after that you will again have solutions. So that solution, if you look at, if you draw a perpendicular from here, and let's say that this is the range for which you are going to have solution. So if you drop a perpendicular here, you will come here, and then it will be flat here, and then you will have something like this. Again, same thing here also. It will be flat here, So this is the next band. Okay. Okay. So again, the way I have drawn doesn't make much sense, because I am supposed to have same distance in the x-axis. Here it is more wider. That's because my parabola is not really correct. So there are some discrepancies here. So yeah, so let me just modify it a little bit. Let me draw it like a better parabola. So if this is so 0, then this is pi by a, then I have to take equal pi by a for the next. Okay, so which will come somewhere like this. This is 2 pi by a, then one more pi by a, if I take 3 pi by a. So then so my parabola should go through these points. So drawing is a little tough for me. Okay, so maybe it is a better parabola. Okay, so what I'm trying to say is that alternatively, okay, so let it be like this. So too much exact drawing is it's not needed. So this is one band, and the next band it will start with here. So now the next band, it will so let me just draw this. So it will be from here to here. Okay, so this is how you have to do. So this is the next band, and same thing, if I do it on this side, I have to, so this is minus pi by a, and then same distance I take minus 2 pi by a, and that will hit on this free electron somewhere here. Then you have to join this. Okay, so like this. The very next band, it will be somewhere here. Okay, so there will be a gap. Okay, now this gap is smaller. Mess it up. So it will go like this. Parabola will go like this. Okay. Okay, I have drawn 3 bands. So the first band is the first region. Okay, so this is band 1. Maybe I will increase the thickness of this, and so this is the first band. The second band is this. Okay, and it is symmetric on both sides. And the third band starts here. Go to. Okay, and the in between regions are the forbidden regions. So you can see the forbidden regions between the first band and the second band. You know, there is no energy states allowed. So these are the forbidden region. This is one forbidden region, and then you have another forbidden region here. This is another forbidden region. So there is no solution for these energies. Okay, but energy can very well be, and also there is a forbidden region at the bottom also. You don't have any states here with those energies. So these energies are forbidden. Okay, you can't take these energies. You can't take these energies. You can only take energies where the band exists. Now, as I said, this is one way of drawing the energy band structure, but now considering the periodicity, so the point here, this point, just after pi by a, and that is basically same as minus pi by a, this point. Okay, so k is equal to pi by a plus some k naught is same as minus pi by a plus k naught. Or you can say that the 0th point and 2 pi by a point, they are same. So for every point, say 1, there is a corresponding point here, because the k value is symmetric. So what we can do is that we can shift this such that the end of this band will come here. So that is an alternate way of drawing. So if I do that, so better I can show this in a smaller space. So that is the advantage. And mostly you will see in books when you draw the band structure, it will only be drawn between 0 plus pi by a and minus pi by a, because everything every other range can be brought into this. So you can basically shift this with respect to 2 pi by a. So if I shift the bottom will remain the same because that is already between minus pi by a and plus pi by a. So so that will remain the same. So that will be like this. Let me just take. So this is the same as before. But the second one, what I'm going to do is I'm going to shift it by 2 pi by a. And that's going to come here. It's going to come here. And then it will be like this. It will come like this. And this one I'm shifting to the right by 2 pi by a. So that will just join with this. Okay. And same thing I can do with this particular one. Here if I shift it by 2 pi by a, this point will come to the origin. So it will come here. And then similarly on the left one, if I shift it by 2 pi by a to the right, then so this is how band structure can be drawn alternatively. So 3 bands, now it's more clear, and this we could do because of the above. What was it? That if you shift bands with by 2 pi by a, actually they are corresponding to same k values. Okay, and why I have shown it here. K0 is shifted by K0 plus 2 pi by a or minus 2 pi by a also you can talk about. So I can put plus or minus. Okay, plus or minus 2 pi by a. Then I get essentially the same wave function. So they are not different k values, they are the same k values. So k is restricted to take values from minus pi by a to plus pi by a. So now you can see that for a given k value you can have various energy so in free electron there is only one energy that electron could take, but in the case of electron or particle in a crystal, it is allowed to take various values. So that is what excited states means. So if you put one electron into the crystal, then with a particular k value, say it can be either here, or the same k value it can be here, or it could be here. So all of them are having same k value. So for a same k value you can have different energies. Say this is maybe corresponding to E1, this may be corresponding to E2, this may be corresponding to E3. Just like in atoms, electron can be in different levels. So here we are talking about same momentum. It can be in any of this and I have only drawn 3 bands. There are more bands which are there. So this vertical axis is basically energy. Okay, so this is energy. So energy versus momentum, this is called band structure, and we have drawn it in 2 different ways. One is called the reduced, the second one is called the reduced k space. Okay, so this is called the reduced k space. Band structure drawn in reduced k space. Okay, E versus K diagram is called the band structure. Okay, so this is another way of drawing EK diagram. EK diagram is also called as band structure. Okay. So band structure is very, very important. So we are now talking about the origin of band structure. Okay, the origin of band and origin of band structure. comes from the conditions that we derived for Schrodinger equation to have a solution in the periodic potential, and the major ingredient into that is basically the block wave function, and because of the block wave function all these things are coming out. We are able to solve it also because of the block function. Okay, so now just like we talked about, for free particle we said about the momentum, we can talk about velocity and mass of these particles. So that's what next we are going to discuss. Okay, now if you look at these solutions, at the bottom part of a particular band, okay, you can approximate it like a parabola. Okay, so I am drawing a parabola here such that it matches well with the bottom part, but then it deviates as you go to high k values, it deviates. So this parabola here I can write an equation, say it is C1 into k square. Okay, just that's the equation of a parabola which is facing upward, where C1 is a positive number. So C1 is greater than 0, that is positive. So if that is the case, then I can talk about the velocity. Okay, so velocity of so I am now restricting myself to velocity of electron or particle at the bottom of the band. Okay, so if you are in this part of the band where you are taking energy or momentum corresponding to the bottom portion of this band 1 or any band, then you can talk about that here also. Okay, the second band also you can talk about. Okay, because these points are basically same as this point, so there is a parabola here also. So any band you take, the bottom of the band, it has a parabolic relationship. Of course, the parabola will be different for different band. The curvature of the parabola may be different, so these constants may differ. So here it may be like another constant C2 into, so this is basically centered around pi by a. So I will have this will be k minus pi by a the whole square. Okay, and the third one again I can, so all of them we are considering the bottom of the parabola. So third band I can again write it as C3 k square. So this way I can give equation for the parabola. So what I am trying to do is that I am because I know that parabolic band structure was the case of free electron, so I am trying to consider it as a free electron and then going to apply the same equation that we have used to connect between the classical mechanics and the quantum mechanics. So velocity of the particle at the bottom of the band can be written as, so what was the expression? So V velocity of the particle at the bottom of the band, so it was 1 by I think h cut dE by dk. Okay, so that was what we said. So if you take this EK diagram or band structure and then take a derivative, that will give you the velocity there. So that is 1 by h cut d by dk, and I have given the equation c1 k square. So let's take it for band, the lower band, c1 k square. Okay. So certain bands are shifted by pi by a, but again, so we will right now don't focus on those details, but let's see what happens if you take the bottom band or the third band. They have similar kind of equation. So then c is positive, so c comes, it's a constant, c by h cut, then 2k, so that's what we will get. So what we are getting is 2c1 by h cut into k. So this is the velocity that we are going to get. Now this velocity, if k is positive, this velocity is positive, because c1 is positive. I already said in the modeling of the band, I said that you can write the expression for parabola is a positive number multiplying k square. It is an upward parabola. Any bottom of the band, it is an upward parabola. So c1 is positive. So therefore, the conclusion here is that therefore velocity v and wave vector so I hope my equation is correct. Let me just verify my equation. Is it by h cut or h cut? Okay. Yeah, 1 by h cut dE by dk. The equation is correct. So the velocity v and wave vector k have same sign. Okay, so that means if you take k positive, there the velocity is positive. So just like the free particle, that is positive values of k corresponds to positive values of v. Okay, so that is number one. Now let's look at again same bottom of the band. We are going to apply the mass of the particle at the bottom of the band. Can be approximated as, okay, because why I say approximated, because this parabola is valid only for some region. It is not valid for you see, it diverges after some point, it diverges from the actual band structure. So the model that we have is only valid strictly for the bottom of the band. So that is why I am saying for those regions at the bottom of the band, it can be approximated as okay. So what is the expression for mass? So we have a relation for 1 by mass 1 by, I will call it as m star, and will become clearer why I say m star. This is not going to be the mass of the electron. It will be deviating from it. So it is going to be equal to 1 by h cut square okay, it is the second derivative of E with respect to, okay, so let me write one more step. Let me put here E, though you know this, it is E, so E is a function of K, and that is equal to 1 by h cut square d square by dk square of c1 k square. So what will happen if you take the double derivative? First derivative, you will get 2k so C1 into 2k, and then again you take derivative, it will be okay. So this is you will get, and this is what you get as positive. Okay, notice that it is positive. Now you may ask, mass is always positive. So that's what I'm coming into. Mass need not be positive always for particles in the crystal. Okay, so in this case we obtained, so mass is basically second derivative, proportional to second derivative. So second derivative is also called the curvature, and so the inverse mass is proportional to curvature. So if there is more curvature, we have less mass. More curvature means 1 by m star is larger, and m star is smaller. Okay, so that's what. So if you have a bigger curvature, you have a lesser mass. So if you look at different bottoms, so you can see that this curvature is very small. So smaller curvature means larger mass. Whereas if you compare with the second curvature, it is more larger curvature. Larger curvature means it comes and quickly goes. That is what larger curvature. Smaller curvature means like this. So this has large mass. So mass differs. It's not constant. It differs with curvature. Okay. So this is smaller, relatively. Okay, smaller mass. So if the energy band has larger curvature, you have smaller mass, because we are equating curvature with the reciprocal of the particle mass, effective mass. It's called effective mass because it's not the free electron mass. It is the mass of the particle inside the crystal. So Newton's law we are comparing, or the classical law we are comparing. When you apply force, the concept of mass is actually defined as when you apply a force, how much is the acceleration. If the acceleration is smaller, we have large mass. Okay, for the same force, if you have large acceleration, then we have smaller mass. So by using that concept, we are defining the mass as mass is related to the curvature of band structure, and this is a very, very important concept. Now I am going into the so this is bottom of the conduction or bottom of the bands. Now I go to the top of the bands. Same concentration. I'll take it for so velocity of particle at the top of the bands. So far I take for so again the formula is same. The connection between classical and quantum picture is given by, so velocity is basically 1 by h cut dE by dk. Now what is the expression for or what is E of k in this case? For the top of the band, if you look at so let's go to this diagram again. Now I need to draw it for the top of the band. So here is the top of the band. Okay, so I can draw it like a parabola of some curve. Okay, so it matches for some region at the top, but then it will vary. So this one I can call it as like C2 dash C2 dash k square, but what should be the sign of k? So if I take C2 to be positive, I should have minus. Okay, so this is the way the constant, or maybe I will take a different constant, say k2, so that I don't need a dash here. So k2, but k is already there. Okay, maybe I will take d. Okay, so d k square with a minus sign, so that d is positive. So d is greater than 0. So d is positive. So if this is a parabola which is facing downward, So we are comparing that with the top of the wall, top of the band. Okay, so it could be here also. There is a top of the band here also, so you can compare it like this. Okay, so this also could be approximating the top of the first band. So this is another band. So, and here is another band. So all the top of the band you can approximate like this. So I will take one of them. So dk minus dk square. So minus dk square. So that's, so this is equal to 1 by h cut 1 by h cut d by dk of minus d k square. So this is equal to minus d by h cut into 2k. Now d is positive, h cut is positive, 2 is positive. So what you can see is that here when k is positive, then velocity is negative, and vice versa. Okay, that is when k is negative, then p is positive. Okay, so for positive values of k, in the top of the band, for positive values of k, it corresponds to a particle moving to the left. Okay, so that's what it means from our result. So this is a bit strange. It should be strange. Now similarly, mass of the particle, this is going to be even more strange at the top of the band. So mass of the particle at the top of the band, again we have an expression that connects classical and quantum. 1 by m star. I put m star because this cannot be electron, because electron has positive mass, but here you will see that we are going to get negative mass. So d square by dk square d of k, and that is basically h cut square into, so if I take double derivative, that means derivative of this, so the k will go, so you will get basically minus 2d, minus 2d. So again you see that this is going to be negative. Mass is negative. If the inverse is negative, then the mass is negative, because d is positive, all this is positive, and there is a minus sign here. So that means it's a negative mass. So what does that mean? If you take Newton's law and say you have a particle with negative mass, you are applying a force to go it in plus x direction, but the particle is actually moving in minus x direction. That's what it physically means. So what is this mean? So these are like some of the intrigue, results that comes out of quantum mechanics. So we are taking the results given by the quantum mechanics and then trying to understand it in a classical manner. So different points in the band, things are behaving differently. So the bottom of the band, they behave like normal particles. Okay, there is a positive mass, and k is positive means it corresponds to positive velocity, etc. That is okay. Whereas the top of the band, when you come, things are behaving very strange. The velocity at the top of the band, if k is positive, velocity is negative, k is negative, velocity is positive, etc. And then more strange is like the mass is going to be negative, and that's completely unconceivable